I guess it was at the beginning of chapter 5, we mentioned area underneath the curve, and I said pretend there's a bottom function of 0, because later we're going to have an actual function that will not be 0, so you have to do minus the bottom function. So here's the idea behind it. All right, so area of a region between two curves. So if f and g are continuous, on AB, and g of x is less than or equal to f of x for all, let me use this symbol here if that's cool. This means upside down A means for all x, and this epsilon means in or element of AB. So for all x in this interval AB, that's all that means, in case you haven't seen that before. Then the area of the region bounded by the graphs of f and g, f and g, and the vertical line x equals a and x equals b is going to be the following. Integral from a to b of f of x minus g of x dx. So you're going to take, this is the top function minus the bottom function if we're doing it in terms of dx. Okay. So example 1. So make a little note here. Top, bottom. And when I say top and bottom, I'm talking about the region that is enclosed by all these graphs or functions. So find the area of the region bounded by the graphs of y equals x squared plus 2, y equals negative x, y equals 0, and x equals 1. Sorry, 1 second. All right. All right, so what you got to do is graph these functions. That way you can kind of figure out what the heck's going on. So we have a parabola. That's no big deal, right? X plus 2, so let's just shift it upward to the start here. Okay, so we know at 0 will be the center of this parabola. So 1, 2, 3. So here is the center of the parabola. Okay, how far is it going? 1, 2, 3, 4. We know y equals negative x is just a 45-degree angle line, but going in the negative direction, going this way. But they're bounding it by x equals, that looks like a y, x equals 0 and x equals 1. So we'll put 1 over here just to make this a little prettier. Okay. So here is my vertical line, x equals 1. At 1, the parabola would be 3, right? 1 squared plus 2 is 3. So I have a parabola going this way. Actually, that's a shitty part. I should do that a little better. The point would be here. Parabola keeps going technically, but we don't need, all we need is this little slice right here. So the region that we're looking at is right here, and I'm going to draw it on the app because this is much prettier there. But you get the idea, right? So got this parabola up top. You get the y equals negative x down here. We got the solid line just going down, up and down forever. X equals 0 is the y-axis, so that's shut it down here, right? So I'm closing it there, closing it here, and up here. So what is the area in here? That's what they're asking. Okay. Let me get the grapher so you can see a little bit better. Okay. Let me delete this crap. I was doing pre-calc earlier. All right, so y equals x squared plus 2. That's a parabola. Y equals negative x. Y equals 0. Sorry, x equals 0. X equals 1. So you see how we have the x equals 1 for the purple line. The green line is right here. So we have this parabola up here that I was trying to graph. A line down there. So we care about this section. So I'm going to put these little points there. Yeah, sit down here. So here's the region. What is the top function? What is the bottom function? Right? So all you have to do to set up the integral is do the top minus the bottom. And what I want you to picture is having rectangles drawn up and down here. So the integral would be, switch back, would be simply the integral from 0 to 1 of the top function, x squared plus 2, minus the bottom function, which is a negative x dx. And the 0 to 1 is chosen by looking at the bounds, right? So right here. So 0 to 1 is where the rectangles are going. So from here all the way to there. So that's why I choose the bounds. So at this point, it's set up. You just integrate and you're done, right? This would be what? Let's skip the integral part. At this point, I'm assuming you can do integrals. And then do the bounds 0 to 1. So that would be 1/3 plus 1/2 plus 2 minus 0. Whatever that is. Who cares? Do you see the idea on how to set it up?
Yes.
All right.
Can you scoot your paper up just a bit
Yeah,
so I can see the points?
sure.
Thank you.
Yeah, there any questions on this first one? Oh, 1 second. Okay, let's go to the next question here. Okay, just remember that top and bottom is only true when I draw a rectangle and I hit both graphs only once. So if you were to hit these graphs, if you were to hit the same graph twice, going along the 0 to 1 interval, then you should probably try switching to dy or separating into different integrals. And I'm trying to think of an example here. Something like, I don't know, let's say we had just because I'm being lazy. It's making up this question. So let's say I said find the area of this region here. You see, if I were to draw a rectangle, I hit this function twice, right? Meaning I cannot use dx. If I go this way, horizontally, that would imply that I'm using dy because my rectangle thickness would be horizontal. So, but if I go horizontal, I only hit it once, so I'm good. Vertical, not good. Right? You see what I'm saying? Compared to this guy over here, um, it was fine because I hit the top function once, bottom function once, top once. So dx was fine. dy would technically be fine, but it would become a real pain because you'd have to shift. You have to create multiple integrals because from here to here, I'm hitting a line. Over here, I'm hitting an axis. And then suddenly I'm hitting a parabola. So each time I shift to different functions, I need to create a new integral. So it'd be one integral from 2 to 3. If I did dy, right? Dy would be a real pain. I would not recommend this. 2 to 3 would be one integral from here to here. Then I have another one from I'm looking at the y, 0 to 2. And then you have another one from -1 to 0. So doing dy for this particular region would suck. Doing dx for this one is just, you just can't. This doesn't work. That's the idea that we're going to explore and try to hammer down right now. Does that make sense? We can do a couple of these. Okay. All right, number 2, find the area of the region bounded by the graphs of f of x equals to 2 minus x squared and g of x equals to x. Okay, so this time I'm not giving you like vertical lines, I'm just giving you two functions. And I'm asking you to find out what the area contained by those two functions is. So you're gonna have to graph it and figure out where they intersect, because once you know where they intersect, those will be your bounds. Okay. So let's see here. To do this all by hand, to find intersection points, you have to set the functions equal to each other. So 2 minus x squared equal to x. Set it to 0, because that's how you solve quadratics, right? We all know this. Factor this guy, that would be x and x plus 1. Actually, let me mess that up.
It's like -2, right?
Yeah, that's what it is. I'm like, this can't be factored. There we go. Thank you. So this would be 2 minus 1. So the intersecting points will be 1 and 0. Okay. So let's start trying to graph this thing. All right, so this parabola, 2 minus x squared, is opening downward with a center at 2, right? So 1, 2. So here's my peak. Alrighty, I'll put 1 and 2 here, 1 and 2 there. At x equal to 0, I have my parabola, and the line would be 0 as well. So I'm going to make a little chart down here. Not that you need it, but just in case you're rusty on graphing. Here's x, here's f of x values, and here's g of x values. So if I were to plug in 0 into the f, you agree that I get 2, right? And g would be 0. If I plug in 1, f would be 1, g would be 1. So, and which we already knew because they intersect here, right? Why did I put 0 there? That's stupid. -2. 2. If I plug in 2, I get 2 minus 4, which is negative 2. Plug in 2 into g, well, it's just a line, so it's 2. Negative 1, I get 1. Negative 1. Negative 2 is the intersecting point, so this one's important. So this guy and this guy are the ones I really care about. Negative 2, let me lower the brightness on this guy. Okay. Negative 2 would be 2 minus 4, which is negative 2. Negative 2. You see how they're the same, right? Which that's what we solved earlier. So of course they're the same. Okay, so let's draw the line. At 0, 0, we have a point. At 1, 1, we have a point. So and technically we should know how to draw y equal x, right? But if you don't, plot some points. Parabola is here, and 1, 1 is there. So the parabola and negative 1 is 1 as well. So it's doing this kind of deal. Okay, actually, let's make that prettier. We said they intersect at negative 2, right? So let's go ahead and plot those points. Ugh, why did I do that? Drawing is not my strong suit, but figure it out. There we go. Finally, I have my region. All right, so the integral will be, right, negative 2, which is right here. No, right here. That's just a line. So it'll be negative 2 to 1. That's where they intersect. That's why I chose those bounds. Top function is the parabola, so put that first. 2 minus x squared minus the bottom function, which is an x, all of this dx. Does this make sense? How we find the intersection points, how we set up the integral.
Yes.
All right. Let me know if you got any questions. I'm gonna skip the integral step because you should know how to do that, but if you want me to, I will. So let me know while I read the next question. All right. And remember, you may just for fun, right? You can use the grapher to help you if you're. I remember when I took Cal 2, I couldn't remember how to graph stuff, so I struggled with this section. Then I had to figure it out because we weren't allowed graphing calculators. But I will let you use it if you choose. So you can see that when you graph both of them, you can find the intersection points pretty easily, right? And since I'm going to choose to do dx, right, up and down, then I will use the bounds of negative 2 to 1. Top function minus bottom function. That's all we're doing. Does that make more sense?
Yeah, that makes sense. You said top function minus bottom section. Is that what you said?
Yeah, so top function minus the bottom function. So basically, you look at the region that's enclosed, and you look at the top part of the region, which is the parabola. So that's first, minus the bottom part of the region, which is the line. So that's where the integral came from here. So this is f minus g. If the line was on top, you would choose g first. But that's only if you're doing dx. If you start slicing horizontally and you that means you're doing with dy, you had to solve for y and for all the functions, and it would be right minus left, which we'll do soon. Okay, this next one is a little annoying to do by hand, so just to save time, I'm going to do this via the grapher so I can focus on this idea here. Find the area of the region between the graphs of f of x equal to 3x cubed minus x squared minus 10x. G of x is equal to negative x squared plus 2x. All right, so let's just graph them and see where the heck they intersect. Save us a little bit of time now that we've done it by hand a couple of times. It's 3x squared, not cubed actually, minus x squared minus 10x minus x squared plus 2x. All right, so here is my functions. The purple one is the first one, right? It goes up and down, cubic-like function, quadratic, of course, parabola. The region that they intersect at is right here. Okay, so actually, no, there's multiple regions, isn't there? There's this enclosed space, right? To this piece and this piece. So we're going to need two different integrals. From -2 to 0, I'm going to do dx for this piece here. Notice how the top function is the cubic, the bottom is the quadratic, and then as soon as we shift over to this region, the top is now the parabola, the bottom is the cubic. So we'll make two integrals. So you're gonna solve two integrals, add them together, and that'll be the total area of this region and that region. Okay, does that make sense? So let's do the first integral here. So the integral from -2 to 0, right? That's the region I'm looking at. Top function is the cubic, so 3x cubed minus x squared minus 10x minus the bottom, which is -x squared plus 2x dx. Does that setup make sense for the first integral?
Yes.
Yep.
Okay, so now plus, right? Technically, we're going to find two of them. 0 to 2. Top function is the parabola in this region. So that will be negative x squared plus 2x minus the bottom function, 3x cubed, minus x squared minus 10x dx. Okay. Any questions on how we form the second integral? We use Desmos to graph.
Why did on the second integral, why did the negative x squared come before this? Why did g of x come before f of x?
So it's all determined by what's on top of the region. So if you look at only this little chunk here, right, this enclosed space, the top part is the parabola. Bottom part is this cubic. So I'm finding this area. That's why.
Okay, and
And
then vice versa.
Yeah, and the other one we had this area. So the top is the cubic, right?
Okay.
That's it. So you integrate that, add them up, and that's it. We'd find out the area of the total thing. Let's see. Skip a simple step here. The integral would be from -2 to 0. These would cancel. Some of these terms would cancel, giving us 3x cubed minus 12x dx. And then you'd collapse this stuff, combine like terms. 0 to 2 of -3x cubed plus 12x dx. And then you would integrate this. So you would get 3x to the 4th minus 6x squared from -2 to 0 plus -3/4 x to the 4th plus 6x squared from 0 to 2. So the area would become, after you do all the number stuff, which I will not do right now, it's 24. Once you plug in the 0 minus whatever. But the new stuff that we're doing is the setup. So setting up the integral is the brand new thing of chapter 7. Everything else after that is stuff from chapter 5 or 6, whatever it was. I think it was 5. All right, let's do one with dy so I can show you what I mean by right and left. And I'll go ahead and graph this by hand so you can see better. This one was just funky, so chose not to. Find the area of the region between the graphs of f of y equal to 3 minus y squared and g of y equal to y plus 1. Okay, there it is. All right, so let's go ahead and graph this. This is going to be a sideways parabola. This is going to be a line. We do need to know where they intersect, so let's start with that. 3 minus y squared is equal to y plus 1. So if we did not use Desmos, we'd have to do this. Set equal to 0, that would be y squared plus y minus 1 minus 3 is minus 2. So this would factor into y minus minus 1, y plus 2. So intersection at y equals 1 and negative 2. Now let's do a chart to help us graph this. Okay. Okay, so this will be my y values here. So I'm going to choose let's think about this. All right, let's try the intersection point, negative 2. If I plug that into the parabola, that'd be 3 minus 4. So that would be negative 1, right? If I plug it into the line, negative 2 plus 1 is negative 1. So they should be the same. All right. I don't need the x there. So I plug in 0 just for fun. I get 3 on the f and I get 1 on the y on the g. Negative 1. Get 2 for the parabola. Excuse me. Negative 1 plus 1, 0. Another asterisk my intersection points. So plug in 1, I get 2 and 2. All right, so here's 1, 2. Here's 1, 2, 3, 4. 1, 2, 3, 4. We know that the parabola for f at 0 is 3. I know this is kind of backwards in case you're not used to using function defined as y. The y value is 0, so the x value is 3. So we have a point here for the parabola. When y is negative 1, the f function, when y is negative 1, we get 2 here for the x. Y is 0, we got that. When it's negative 2, we got negative 1 for the x. So here. All right, so the parabola is doing something like this. All right, y plus 1, plug in 0, we got 1 for 1 here. And I plugged in negative 1 into the y, I got 2, well, I got 0, so here. I plugged in negative 2. I got negative 1, so here. Those are right, 0. Hold on, I think I drew that weird. It's supposed to be. I think it's just my scale, stupid. So G is negative 1. For negative 2 on the y, we have negative 1 on the x. So negative 2 should have a point about here. This is a little low. Okay. So they both intersect here. Parabola technically goes this way. The line goes this way. Anyway, I really effed up this drawing. It's really ugly. Okay. But anyway, now that we have it drawn, at least a sketch. It's not to scale anymore. But you can see that if I were to go up and down, I would have an issue with a rectangle here. So I need to slice this way. And the thickness of these rectangles is dy. I cannot go up and down because I'll hit the parabola twice. Okay. So let's look at our prettier version of this, pretty picture. So just change it to x equals instead of f of y. It's easier. 3 minus y squared, x equals y plus 1. All right, so those are the intersection points we found. So we will integrate from -2 on the y, because we're doing dy, all the way up to 1 on the y value here. That's how we find the bounds. So the integral from -2 to 1, the parabola is on the right, so right minus the left, right? Right minus left, so 3 minus y squared minus the line, which is y plus 1. So once you have the intersections and you know what's on the right and the left, you can pretty much create the integral, right? So right side minus left side from -2 to 1 using these guys. So the picture doesn't have to be perfect, but it helps a lot to have it. You guys have any questions on number 4?
No. No.
All right. Let's see how much time I have left. Let's go ahead and start the next section. If you have no questions on 7.1, we're going to move on to volume. All right. 7.2, volume. The disk slash washer method. So let's talk about the disk method. To find the volume of a solid of revolution with the disk method, use one of the formulas below. Okay. So when you have the rotational axis of that is horizontal, you will use this formula. And I'll explain what that means in a second. The volume would be equal to pi times the integral from a to b of r of x squared dx. So basically picture, let me see if I can draw you a picture here. Say this is your x-axis here. And you have some region from A to B. some, I don't know, some function, whatever. Right? So we want to know if I were to slice vertically, well, actually, I should rephrase this. So what's going to happen is you're going to spin this shape, this region, around and around the x-axis. So picture like an after image happening as you spin it, which creates a solid. So this would be kind of like a, I don't know, kind of somewhat like a cone. See what I'm saying? As you go around and around. I picture stacking a bunch of these around the axis, creating like a circular piece. All right. So if I'm rotating this way, then I'm required to slice this way. If I'm using the disk/washer method. So this forces you to use a specific method depending on how we're rotating. So if I'm rotating this way and I want to do dx, then I have to do disk. Okay. Now, if I have a vertical, and it doesn't have to be x, it could be just some random horizontal line that I'm rotating on, some horizontal axis. Vertical axis of revolution. I said rotation earlier, but whatever. Should be revolution. That formula would be very similar, except you switch to dy. So from C to D of R of y squared dy. So this is D and C. Let's say your function is doing something like this. So you have some region here. So your rectangle would be left to right. Okay. So if I'm rotating on this axis here, horizontal, vertical, I'm sorry, a vertical axis, then I have to slice this way, which makes me do dy versus this is dx. Okay, does that make sense? So the rotational axis basically tells you which technique to do. Currently, we only have one technique, which is the disk or washer method. And we call this this radius here. We call that r of x. Okay. The height of the rectangle r of x and r of y are perpendicular. So that's the key here. To the axis of rotation. or revolution, whatever. For this method, the entire region touches the axis of revolution and therefore upon revolution the solid is formed with no hole or bowl kind of shape. So since the axis is touching the entire region, there's no donut shape formed when you're spinning around and around. All right, so if it's not touching the axis of rotation, this r of x, this radius, then you'll have a gap, which creates a hole when you're spinning around. When that happens, so when you have a hole, use basically it's the same formula, but it kind of compensates for that missing piece. Use pi equal to integral from a to b of r of x squared minus little r of x squared dx. Where capital R of x is the outer radius and R of x is the inner radius. Sorry, I'm not on the screen there. And of course you have similarly, there's the y version, which is not too different. Anyway. Okay. Let's do an example. If I can find one. Here we go. One moment. Find the volume of the solid form by revolving the region bounded by the following graphs. Or the graphs of f of x equal to square root of sine x and the x axis from 0 to pi about the x. So first thing is graph it. And whenever they say about, they're talking about the where they're rotating. So they're rotating this way on the x. Okay. So square root of sine x is basically just this here. Here's 1, 0, pi over 2, 1. Oh, I'm sorry, pi. So 0 here, 1 there, 0 here. Sine looks like this when you square root it. Missed that point, but whatever. Just make it bigger. Okay, so this is the region I'm going to spin around. So I'm going to spin this around and around, which forms like an egg kind of shape, right? So you draw your rectangle. Since I am rotating on the x, my slice needs to be perpendicular. Dx. That makes sense? So this determines the slice. The slice determines dx. So I need to do the integral from, since it's dx, I look at the x-axis, 0 to pi. Top function, square root of sine x squared. There's a pi in front of this formula. I forgot about it. Minus 0, because there's no gap, right? Top is this, 0 is the axis, dx. So the integral becomes simply integral of pi sine x dx from 0 to pi, which is going to be negative pi cosine, right? From 0 to pi. So the answer would be 2 pi. So the volume is 2 pi. Is there any questions on the setup or how we did this? Okay. All right. Yeah, you know what? Yeah, let's do one more and then we'll call it a night because it's a lot of stuff already. I'm having trouble focusing myself. All right. Example 2. You guys are cool on the first one, right?
Yes.
So find the volume. It's the same question. Of the solid formed by revolving the region bounded by the graphs of f of x equal to 2 minus x squared, g of x equal to 1, and rotated about y equals 1. Make sure I got that right. Second. Yeah, there's nothing wrong with this. Okay. So the graph will be, if I plug in 0, I get a 2. So my parabola is right there. If I plug in 1's right here, 2's right there. So somewhere around here, it hits the x-axis, square root 2. Y equal 1 is right here. Something like that. So intersection points, they're going to be the bounds. So I'm going to integrate from, since I'm rotating on this line, I'll be slicing perpendicular to it. So it's going to be dx. So integral of the top function minus the bottom function that will be, so that idea still applies here. 2 minus x squared minus the bottom 1. This is y equals 1 line, right? Squared. The bounds will be where they intersect. So where do they intersect? So to find the intersection points, you'd set them equal to each other. Set it to 0. Oh, that would be what? Minus 1. Yeah. So x is 1 and negative 1. So negative 1 to 1. So my graph is not to scale. That's not where, it doesn't actually intersect way out here, but that's okay. Let's graph the prettier function. Okay, y equals 2 minus x squared. Y equals 1. So there's the region we were talking about. From negative 1 to 1. So that's where it's supposed to connect. From on my graph, it looks like it's 1.4 or something. But who cares? So integrate from, since we're doing dx, negative 1 to 1, the x values. Top minus bottom. The bottom is a line of y equals to 1. That's where this integral came from. So that will become 2 minus, actually 1, 2 minus 1 squared. And then that's it. Just integrate that. And then you'll get, I don't know, some area nobody cares about. But do you see the idea? Forgot my pie. Okay. If you're doing with a hole in it, make sure you subtract the inner radius. I think we should do one of those real quick. Shoot. Yeah, sorry. Let's do one more and then we'll call it. So you can start the homework whenever you want. So similar question. Find the volume. Formed by revolving the region formed by y equals square root x, y equals x squared, and rotated about the x-axis. All right, so your picture is going to look something like this. I'll try to make it pretty this time. Here's 0.5. Here's 1. Here's 0.5. Here's 1. Oops. All right. Square root function is 0 at 0. The square root function is 1 at 1. So it'll do something like this. Parabola is 0 at 0 and 1 at 1. So it'll do something like this. And we get this shape here. So if I'm rotating about the x-axis, that's when you start to see the hole. So we have this outer radius and this inner radius. Hold on a second. Make sure I drew that right. The inner one would be, yeah. Sorry, I think I drew that wrong. Yeah, no, actually, it was fine. I'm sorry. Just doubting myself. So this rectangle, this radius from top to bottom, that is big R. Let me place that better. From this bottom part here, that's little r. And this is big R here. Does that make sense? That little gap at the bottom is little r. In other words, that's what's causing the hole. So when you spin this around, you're going to have a gap in the middle, which needs to be subtracted to find the correct volume. So the integral will still be from 0 to 1, since we have already gave you the intersections here. So you're going to have pi, part of the formula, the outer radius of big R will be the top function x, actually square root x minus 0, all the way down to the axis of rotation, minus the one that's causing the hole, which is x squared minus 0 squared. Okay. Does that make sense? How this is r of x and this is little r of x? This is the difference between disk and washer. It's really the same formula. It's just when you have a hole, it kind of you adjust and shift to a washer method, which is the same crap. You're just subtracting the inner radius. Okay. Well, at that point, you just integrate. It's not a big deal, right? So this would be x minus x to the fourth dx, which will be pi times x squared over 2 minus x5 over 5 from 0 to 1, which will give us 3 pi over, what is that? 10. All right. So I want to make sure I did one with a hole before we call it a night. All right, guys. So it's this about 90% of 7.2. So next time, I'm gonna let you try to digest this and think about it. Mastering 7.1 will help you understand 7.2. So since we haven't had much time to do 7.1 yet, 7.2 might seem difficult, and if not, great. But anyway, I'll stop here, and I'll see you guys on Thursday.
Thank you.
Thank you. See ya.